Okay.
Okay, so we just observed ice melting. We took the temperature of the ice every 30 seconds. And we observed that essentially during the phase change, ice melting into a liquid, solid to liquid, we did not see a temperature change associated with it. Even if we added heat with our hands to the beaker, we still did not see the temperature really changing a lot. We ran out of propane before we were able to boil the water, but we did see that as soon as all the ice was melted, the temperature started to change. And the liquid water was able to change temperature. If we had been able to get to a boiling point, we would have then seen that the temperature would have stopped at right around 100 degrees Celsius, and it would have stayed there until every last bit of liquid water had converted to a gas, and that phase change was complete. But why is that the case? Well, there is no temperature change during a phase change because all the energy moving into or out of the system, and in this case, our temperature is increasing, so all the energy moving into the system from the surroundings is being used to complete the phase change, to melt the ice or to boil the water. And so there's no energy available to change the temperature during a phase change, because all the energy is going to complete the phase change. It's not available to change the temperature. So until there's enough energy to melt all the ice, the temperature won't change. Until there's enough energy to convert all the liquid water to gas, the temperature won't change. So that's a key point to discuss among many other things in your discussion. Now, when we graph our phase changes, we see that there's really a flat, kind of hardly any changing until, and you want to mark on your graph that place where all the ice was melted, and that was somewhere right after the 20-minute mark, I don't remember. And then you'll see that temperature increase until you get up to 100 degrees Celsius, and then you'll see it level off again at the boiling point. So no temperature during the melting phase change, no temperature during the boiling phase change. But when the water is liquid and energy is being added, the energy is available to change the temperature because there's no phase change happening. So while you were doing the lab, you were supposed to be thinking about writing the procedure. What am I doing? So what kind of procedure would we want to have for this lab? Let's think about a few of the things and make sure you guys start to understand how to write the procedure. So what was the very first thing that we did?
We ground the ice and poured it in a beaker with water.
Okay, so instead of saying we ground the ice and poured it in a beaker, how would we phrase that? The ice was ground up, or the ice was ground, so maybe, yeah, and you want your procedure to be in a numbered step. That's the only real part of the lab that you're going to have numbered steps. For the materials, you can just make a list. If they're numbered, that's fine. If they're not, if they're just like a list in a row, that's fine too. The ice was ground and put in a beaker with some water. During the procedure part, you never have to explain why you did something or make observations about what that looked like. It's just literally what you did, not why or how or anything. Then what?
We would stir with the thermometer.
Okay, did we do anything between that? Probably not. So. A thermometer was used to stir, is that okay? The ice, water, mixture. And then what?
Temperature readings are taken every seconds.
Readings, and no abbreviating for you guys. Were taken every 30 seconds. And then then 25 minutes passed, and then so here's a key point about writing your procedure. Where it deviates from the expected procedure is important to note. So what did I do at the 15-minute mark or so?
You removed some of the ice.
So, some was removed by a hot object, like my hand, but we want to keep people out of it, so and like if you know what time that was, or if you could see a change. If you don't know what time it was, take a guess, which 15-minute mark or whatever. If you know which data points it was between, that would be a good thing to know. I should have mentioned to write that down. Then, maybe beaker was warmed for last 10 minutes of ice melting or something like that, because we added our hands around. And then, how would we phrase when I started to heat? Let's see. I was heating.
High-level object.
Beaker was heated over burner, maybe. And then until burner malfunctioned, I guess. Different than expected. Some of the greatest discoveries in science have been made when the procedure was done incorrectly by accident, but because it was recorded in the way that it was done instead of the way it should have been done, they were able to recreate, test out, and figure out what had happened, and then from there came up with some pretty interesting scientific theories. So it's really important to write down what you did, even if I stuck my hand in it or spilled it or messed it up. You should always record what you did. It's an important habit, and it's good ethics. Because if you messed up the experiment and your professor gets all excited because you just did something awesome, you need to know that you made a mistake. So you can either recreate it or throw out your data because you did something wrong. So writing the procedure, make sure it's third person, past tense, passive voice. I would type it because if you have to make corrections, it's really hard to make corrections. And then you have to handwrite the whole thing over, and if I have to make it corrected twice, then you have to write it again, and that's no fun. So I would definitely type it. You want to have all the parts of the lab report, including materials. You have your data section, and you need to attach a graph. That was not enough, was it? That's not good. Okay, so there are a few really important things I need to tell you about what you're going to do next week. Now, you do have videos on YouTube for calorimetry with the extra calorimetry sheets. But here's, in a nutshell, the basic calorimetry theory. So calorimetry is a way to measure heat and heat change. So next week we'll do an experiment, and here's what will sort of happen in a nutshell. You'll have a styrofoam bowl, because styrofoam is a great insulator. In calorimetry, the whole goal is to insulate your system from the outside environment so that no heat can get in or out. That's why we use styrofoam for coffee cups, right? We don't want to lose all our heat and end up with cold coffee. We're going to keep all the heat in that we have. So we're going to conduct this experiment inside a very insulated system. We're going to keep it as insulated as possible. The point of calorimetry is, so we'll have some water in here, and we know lots of information about the water. We're going to add some hot metal. We'll heat that metal up in boiling water. I'll actually have a new propane tank, so you can boil the water. And then that boiling water we know is 100 degrees Celsius. It will heat the metal to 100 degrees Celsius, exactly, right? And we'll put the metal into that water, so we know the temperature that the metal is, we can measure the temperature the water is, we can measure the temperature changes. And here's the key point. We know that all the heat that went into the calorimeter can't get in or out. No extra heat can get in through the styrofoam. No heat can get out because the styrofoam is an insulator. Now that's a source of error, of course, because it's not a perfect insulator, but it's very good. So all the heat that the metal loses, the water must gain, right? If you put a hot metal into a cup of water, then you insulate it. All the heat that the metal loses, the water must gain. Okay, the heat can't go anywhere else but to the water. So the experiment's over when the metal and the water have come to the same temperature. Okay, that's a key point to know about calorimetry. Now, when you read the next part of the chapter, Q is heat. You want to write this down because when you're reading it, it's kind of hard. Q is heat. It'll be measured either in joules or calories. Okay. M is going to be mass. You'll need to know the mass of everything. The calorimeter cup itself, the water in the cup, the piece of metal or glass or whatever you're testing out. You need to know the mass of each individual thing. C is another variable you're probably not familiar with. It's called specific heat, very different than heat. Now you guys know the definition of a calorie is the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius, right? Specific heat is the amount of energy required to raise the temperature of a substance, 1 gram of a substance 1 degree Celsius, right? So water takes a huge amount of energy to heat up. It has a high specific heat. In fact, a familiar number. This is the specific heat of water. And that's a number you want to memorize. It's exactly the same as the conversion factor between joules, because we know water, to raise it 1 degree Celsius, 1 gram of water 1 degree Celsius is 1 calorie. So for joules, obviously, it's this very familiar number that's the conversion factor between calories and joules. It has these complicated units. Units are very important. You must use them to cancel out joule per gram degree Celsius. So you must include units in all the problems. Of course, you can see a Q, heat, is in joules. And mass, of course, is going to be in grams, right? Then delta T, just like we talked about today, the change in temperature. That metal is going to go from 100 degrees Celsius down to maybe 30. So its delta T would be, negative 70 degrees Celsius. The water will go from room temperature, maybe 25 degrees, to the same temperature as the metal, 30 degrees or something. So the water might go a positive 5 degrees Celsius as its change in temperature. Here are some key points that you have to know about doing these problems. The final temperature, delta T is equal to the change in temperature, the final temperature minus the initial temperature, right? The final temperature of everything, write this down, is the same. The calorimetry experiment is over when the metal, the calorimeter, and the water are at the exact same temperature as each other. Everything has to be the same temperature at the end, okay? T initial is the same for water and the calorimeter. Water and the calorimeter are always going to have the same temperature readings as each other. The metal is the same as they are at the end of the experiment. And even if the problem doesn't tell you, see the specific heat of something, you know. If it's water, it's this. If it's something else, there's a chart in your book that tells you the specific heat of lots of metals and glass and different objects. So if it doesn't tell you C for something, look at the chart. Don't just say, oh, I don't know how to do this. Okay? These problems get really complicated if you don't lay them out very carefully. That's why I gave you the extra calorimetry sheet. Those extra problems, does anyone have one laying around? Or maybe I can find one real quick. But if you look at that extra calorimetry sheet here, Saul, pass one? Saul? Yeah. Okay, so you want to make a table for every single calorimetry problem. You want to write down all the information you know for each thing, whether it's the metal, the water, or the calorimeter. If you don't make a table and lay out what you know, and you don't remember that you do know the specific heat of things, then you might get confused. So if you do get confused, watch the videos that I'll email to you that are associated with that worksheet. But remember, Q is heat, C is specific heat, totally different. Heat is in joules. Specific heat is for each individual type of material. It'll be different. An intrinsic property like density that helps you identify, in fact, a given material. Now, am I out of time? not out of time. Let's look at practice problems. Okay. So, review questions. Look at those. We go to 10 o'clock, right? I have 8 whole minutes.
For module 1?
Module 2, review questions.
Oh, you can,
So every single week, you look at your homework on the syllabus that I gave you on back to school night.
oh, well.
September 2, it says Module 2, read to the top of page 49. On your own, 1 to 3, review question 1 to 6, practice problem 1 to 4. Every single week you have homework according to the syllabus. I will not tell you your homework because I gave it to you on a piece of paper. I will not remind you because you are old. But that always happens the first week. So remember, it's always there on the syllabus. So review question number 1. A man pushes a stalled car for 2 minutes. During the first minute and a half, the car doesn't move. For the last half a minute, he pushes harder and he does get it to move. Is the man doing work for the whole 2 minutes, Brittany? No. When is he doing work?
When the car started moving.
Yep, as long as the car's moving, he is doing work. Liam, classify each of the following as potential or kinetic or both. A lump of coal.
Potential.
Potential energy has energy stored in the chemical bonds you can burn up and liberate. If the coal is up here, though, it has potential energy to fall. How about, oh my, not Julia. I can do it, I can do it. No, I can't, you have to tell me.
Maddie.
Maddie. Okay, Maddie, how about a flash of lightning, potential or kinetic?
Kinetic?
Sure. Saul, candle flame? And then I'll let you ask.
Could be both.
Probably
Or
fire.
just the flame,
Yeah.
and that'd be kinetic.
Yes, the candle itself will have potential, Liam,
Why is it just kinetic?
because we're lying to you and beginning chemistry. Sorry. That is a lie, you're right. A tornado, Lily?
I put kinetic and potential because I don't know. I was in.
You can make a case for both, and it's good in questions like this on the test to make a case. So for potential energy, what kind of potential energy might a tornado have?
The cow said it picks up and run out. I don't know.
Yeah, for real. Like all
Oh,
the
okay.
debris is up there and it has to fall eventually. So there's potential energy. And kinetic would be obvious, the wind,
The actual.
movement, yeah. Let's see. So Jolene, a chemist watches the temperature of a vat of liquid and notices it decreases over time. The temperature is decreasing. So what does she conclude?
The heat is moving.
Where is he going?
The colder place, wherever.
So if this is decreasing in energy, then, like say, well, my hot tea is decreasing in energy. So heat is going from where to where?
Out.
Okay, so there was lots of
Into
heat
the-
in
into the-
here.
The side. I don't know.
Right, so heat is going from the hot place to the cold place, leaving here to here. So the temperature in here is going down. And what that actually means is my hot tea is heating up the room because it's losing energy to the room. So tea gets colder, room gets hotter. But the room is big and the tea is small, so you don't notice. If we put a bathtub full of hot water in here, we would notice that the room was getting hotter as the bathtub got colder. Let's see, number 4, Jen. A hot object is totally insulated from the outside world. Will its temperature ever change?
No.
No, it won't. Temperature never changes if you completely, and that's our goal in calorimetry, is to keep all of our energy inside the calorimeter, not allow any contact with the outside world. Oh my gosh. What's your name?
Austin.
Austin, I knew that. Oh, it's gonna take me a couple weeks. Austin, Erin, Grace, Kristen, Micah, Maddie. I'm good. Austin, sorry. Should we ever look to science as absolute source of truth?
No, because science is infallible and can contain error.
Science is fallible.
Oh yeah. Okay,
God is
and then
infallible.
yeah.
So we make mistakes as humans. We get it wrong. Things that we have thought for years we were really right on. And once again, like Liam just pointed out, I'm gonna tell you a lot of lies this year, because the truth is too complicated even for me to understand in some cases. Molecular orbital theory is immensely complicated, and the truth is too much. So you learn in steps. You learn what you can handle now, then you take some calculus, then you learn a little more truth, then you get a PhD, and you learn that that wasn't entirely true either, and then you discover new stuff that nobody knows yet. So, science is always growing in its understanding of what God has done. Aaron, heat is added to two identical objects. So let's say these two beakers that are not full of anything. They're initially at the same temperature. The first absorbs 100 calories and the second 100 joules. Which gets hotter?
The one that absorbed the calories,
Why?
because
Calories are...
calories are more energy.
7 minutes. I'm sorry, I didn't mean to interrupt you. Quick question though, did everybody receive an updated student contract last week and sign one? If you didn't, just continue. Great, thank you.
Hold on, Mrs. Shute. Before I trip on everything. Can I give you stuff right now?
Oh, absolutely.
Do you want the box tops or is that somebody else?
Oh, I'll take those too.
Sorry.
And
I know I won't
put
get to
those
see
together, but
you.
I will take and give
Still
you.
recording.
Oh. Hi, everyone. This is Mrs. Shute. She does so much for us.
Hi.
And
And these
all
actually help to pay for your microscope, so please save these up. Because this is
That
what
is a
we
good
bought
public
2
service
microscopes from,
announcement.
so thank you,
Oh.
yes.
Yes. Bring the box tops because I really think she's going to give me that money next year. And then we won't run out of so yeah. Okay. How many of these review questions did you guys do?
1 through 6.
1 through 6. Okay, so that was it. The rest of these are just kind of energy conversions of the kind that we did a few here. You did 5 practice problems this week? How many? 5?
4.
4. Okay. And she just said I have 7 minutes?
Yes.
That can't be right, but we'll do. Okay. Jen, did you get zoomed in on the board at all? Zoom in real quick and then I will.
I have at some points gotten zoomed in on the board.
All right. So I wanted to give you that introduction to calorimetry because it can be really confusing if you just read what he wrote in the book and you've never seen anything like it before. People really struggle with it. Definitely start doing your homework early in the week so you have plenty of time if the crisis arises. Convert 15 degrees Celsius into Fahrenheit. And that's 3 significant figures. We want to convert to Fahrenheit right now. So Grace, what is the equation I would use? Convert Fahrenheit or Celsius to Fahrenheit.
You would multiply it by 96
Okay, so
and divide it by, multiply by 9, divide by 5.
is this good? Okay. Then I'll plug in here. I'll multiply that, and then I'll just add 32, and that would rearrange it. And what do you get?
59.0.
Now, a key point, she gives me that 0.0, that's exactly right. Even though this 32 doesn't have a tenths place, it is like a perfect conversion factor. So you don't account for its significant figures, you assume it has infinite amount. So since this ends in the tenths place, these are perfect numbers, that's a perfect number. So you're gonna keep these 3 significant figures in the answer. So 59.0 degrees is exactly right. Let's see. The temperature of deep space is 3.5 Kelvin. What is that in Celsius and what is that in Fahrenheit, Kristen?
In Celsius, it's negative 269.7.
Okay, so Kelvin never gets below 0. Like we can have below 0 in Celsius, below 0 in Fahrenheit. Kelvin never ever goes below 0. So that's something that you can use to check to make sure that you, what am I doing, are always going to be okay. So if you convert and you go from Celsius to Kelvin and you get a negative answer in Kelvin, you did something wrong. Kelvin ends at 0, never goes negative. Well, it never gets to 0 either. It just approaches 0 very closely, we think. There's another one of those moments where probably it never does that. So, what did you say was for Celsius?
It's negative 269.7.
And notice you rounded to the tenths place because this is significant in the tenths, that to the hundredths, so you have to round to the tenths. And how about Fahrenheit?
Negative 453.4.
4. Okay, so that's for Celsius, you just subtract 273.15. This is for Fahrenheit, and you're always gonna have the same place of significance when you convert for those, so that's right. 453.5, I get 0.5, but I don't know.
I got 0.5.
Maybe 453.5. If you have the right number of significant figures and you're pretty close, it's unlikely I'm gonna take off an eighth of a point or whatever I take off. So that would probably be fine. It's probably 0.5, but, yeah. Let's see. Number 3 for Micah. Some parts of the western U.S. regularly reach temperatures of 115 Fahrenheit in the summer. What is that in Celsius?
Well, that would be 115 times 9/5, because you would reverse the fraction. Then you would subtract 32, right? No, you would add 32, and then you should get the answer. And I've been to California, so I do know.
Does it really?
It actually doesn't feel as bad because there's no humidity.
Yeah, dry
So
heat.
tell me what you got when you did that.
Okay, if I do that, then I get
Everyone,
175 degrees in
Okay.
Fahrenheit.
in Celsius.
Oh, we're doing, yeah, Celsius.
So you want to think that through. Water boils at 100.
Oh, sorry, I inputted it wrong.
Right, and so when that happens, it's good that that happens in class sometimes because you've got to think your answers through. If you get that the room temperature is hotter than boiling water, you know that's not the case. So think again, like think your answers through. Don't
So
just
it'd be
say,
about
oh, it must be
46
right.
degrees
The
Fahrenheit.
mile.
That's right.
The miles question.
Yes, well, Jenny already took that test and I graded it, but every year I have some people on this first test say a football field is in excess of several miles or kilometers or something, when they do that conversion on the football field problem. And, you know, you just make a conversion, you make a mistake, you don't think through, no, the football field is not more than some number of kilometers, it's less than a kilometer, right? It's not that big. And so if you don't think, that's a problem. Converting calories to joules, you just do 1.18 or 4.184 joules per calorie. So we did a lot of that, I think we're good. So finish module 2, don't wait, start early.